All right, if you are on Zoom, please type something into the chat to let me know that you're here. The roll sheet is floating about for all those people who are physically present. We got a fair amount of material to cover today. We're going to be talking about Cascode amplifiers, and if we get through with that, I've got a couple of pages of notes on current mirroring that we can talk about, and we'll finish up that topic on Friday, I believe. So, with that in mind, all right, we're on page 1. Let's get cracking. So, our big topic for the day is the Cascode Amplifier. And our first miniature topic of the day is going to be what's known as short circuit transconductance. All right, so when we were talking about BJTs and Mosfets, we introduced the concept of transconductance and defined it as a transistor's ability to generate an output current due to a small change in its input voltage. So for BJT technology, we defined our transconductance as our change in collector current caused by some small change in our base emitter voltage, and we found this to simply go to IC over VT. And for MOSFETs, we defined our transconductance as the change in the drain current divided by the change in the gate source voltage. And there were 3 or 4 different relationships that we got for the transconductance. I'm only going to list the kind of base one for saturation region operation specifically, because that's where we typically want our circuits to operate. So in each case, our output quantity is a current, and our input quantity was some voltage. So we can generalize the concept of transconductance really to any type of circuit where we apply some input voltage and have some output current we can measure, be it an amplifier or not. So generally speaking, if we have a generic linear circuit where we apply some input voltage we can define the transconductance of this circuit as capital GM is equal to the output voltage, the output current divided by the input voltage when we short out our output terminal. So this is what our short circuit transconductance is going to look like. I want to make it very, very clear here that the direction of our output current for this measurement is that that current is flowing into the output node. That's going to be very key momentarily. All right. So this short circuit transconductance, capital GM, represents the circuit's ability to convert an input voltage into an output current. And we can actually use this relationship as a different way to interpret how we've been looking at voltage. So if we had a generic black box circuit, let's just call it a simple amplifier or something like that. Here is our input signal. Let's go ahead and go down to here. I'm going to put a node here, plus V out minus, and this node is ground. We could use Norton's theorem to represent this circuit by its Norton equivalent, right? We have a linear two-terminal network. So we can represent any linear two-terminal network using Norton's theorem as a current source in parallel with a resistor, right? So from Norton's theorem, I can make that circuit look like this one. Here is I out. Oops, not what I wanted to do. I apologize. Like so. So let's talk momentarily about first, why we have I out with this particular direction. So if we short circuited this guy and measured the current flowing in, which is how we would go about determining the transconductance, we would see that we would measure this exact current I out, and it would have a direction down because it was flowing into the output terminals. Now, when we have our original circuit open circuited, and we're trying to find its equivalent resistance, or Thevenin resistance, or Norton resistance, or whatever you want to call it, what do we do to V in again? When we're trying to find the Thevenin resistance directly, we have to turn off all of our independent voltage sources, so we would short it out. So the resistance that we are looking for is actually the exact same thing as the output resistance of all of the amplifier circuits that we've been looking at. We short out our input voltages, we turn off all of our DC sources and all that kind of stuff, and we're looking in through the output terminals. So this resistance right here is nothing more than the R out that we have, hopefully at this point, effectively beaten to death on how to figure out, okay? This output voltage, V out, where we have our ground, no, go away. Sorry, my finger keeps touching stuff. Our ground here, just for reference, just using good old Ohm's law, is nothing more than negative I out times R out, right? We have an open circuit. The current is flowing into the negative polarity terminal as it makes its loop, which is where the negative sign comes from. Ohm's law tells us that the magnitude of the voltage is just I out times R out. So nothing remotely fancy there, just good old circuits one stuff. So recognizing that I out is equal to GM times V in, this gives us V out is equal to negative capital GM V in times R out, which means our voltage gain, AV, by definition, V out divided by V in, is simply negative GM, our short circuit transconductance, multiplied by R out, the output resistance of our circuit. And this works regardless of the type of amplifier or anything that we have. So we're going to use this to determine the voltage gain of a cascode amplifier because it's a little bit more gnarly than doing it directly, for sure. As kind of a proof though, I'd like to take a moment to look at a single stage amplifier that wasn't in the textbook, it was considered too difficult to do according to the textbook, and prove that we get the exact same result. So let's look at a common base amplifier. The textbook's proof uses a common emitter amplifier with the early voltage effect, or the early effect being neglected, and it's so trivial as to be almost pointless. So I decided to step up the game a little bit and do something a little bit more difficult. And if it works in these two cases, we can argue that it's probably going to work in most. So here is our common base amplifier, right? We're applying a DC signal to our base terminal. Input is at the emitter, output is taken at the collector. So method one, how we beat this to death, or these types of circuits to death, in 335 would be to draw our small signal model. Oops, let's do it here. MV pi or not, because we're not going to punk out and ignore the early effect, since we haven't been ignoring it at all for our cascodes. Here's our signal V in. Here is V pi. This is R pi. Base, emitter. Here is our collector. And between the collector and ground, we have our resistance RC, and this is the pin at which we measure our output voltage, V out. So just looking at this guy real quick, it stands to reason that we can see that V out is the exact same thing as the voltage drop over that resistor RC, since V out would be measured with respect to ground. Positive polarity terminal would be on top, negative polarity terminal would be down here at the ground. The current flowing through RC, so let's write this down real quick. V out would be RC times the current flowing through RC, and I'm arguing that the current that flows through RC is going to be negative the current that's being supplied by this dependent source minus this current flowing through that resistor R naught as well. Just applying Kirchhoff's current law at that particular node, which gets me negative GM V pi RC plus V in minus V out over R naught times RC. And I can do a small amount of algebraic manipulation here, noticing that Vn is exactly equal to negative V pi. And this would lead me to a gain relationship of AV is equal to, go away. Go away, there we go. GM RC plus RC over R naught divided by 1 plus RC over R naught, which I can simplify to be RC over R naught plus RC plus GM R naught RC over R naught plus RC. And if we were to neglect the early effect, this would simplify to positive GM RC, which is exactly what we would expect for a common base amplifier. So method one, honestly, not particularly difficult. Don't know why the textbook was like, let's leave the early effect alone because it's too dang hard, when it obviously really isn't. Let's look at methodology number 2. First step would be to calculate R out. So for our circuit, that would mean we short out our input, which was applied at the emitter. So our emitter is grounded. Here we have GM V pi, our early effect resistance, base emitter collector. Between the collector and ground, or really VDD, we have this resistance RC, and we are looking into this terminal. So who can tell me by inspection what the output resistance of this amplifier configuration should be? R naught in parallel with RC, absolutely right. V pi has to be 0, which means this current source is an open circuit, and so we just see these two resistors in parallel with each other. R naught in parallel with RC. Now we would need to calculate the short circuit transconductance. And so to do that, look at our small signal model again. This time our input is being applied. So we have voltage Vn here between our emitter and ground. Here's our base. Let's see, R pi, V pi. Here we have our resistance RC, and then we short our output terminal and measure the current flowing through the short circuit. So this allows us to observe something pretty easy, right? If this node is ground, that means this node up here is also ground, So no current can be flowing through that resistance RC, which gives us I out is simply going to be the current flowing down this way. So GMV pi plus the current flowing through that resistance R naught. So that would give us, let's see, GMV pi, where V pi is still exactly equal to negative Vn. Everybody can see that? So that's going to give us negative GM Vn. And then our current flowing down through our early resistance R naught here is 0 minus Vn divided by R naught, or negative Vn over R naught, which gives us a short transconductance of negative GM plus 1 over R naught. So easy enough to determine. Our last step then would be to calculate our voltage gain. Voltage gain is negative GM R out, which is negative times negative, so positive GM plus 1 over R naught times our output resistance R naught times RC over R naught plus RC. And just doing a little bit of algebra, we get RC over R naught plus RC plus GM R naught RC over R naught plus RC, which is the exact same result we got doing the regular or 335 voltage gain calculation. So for these single stage amplifiers, everything seems to be working out well. This is an example much more difficult than the one that's shown in the textbook. We are getting the exact same answers, regardless of which way we determine our voltage gain. So I'm going to argue that the proof shown in the book is good enough, even though they don't really actually show a lot of proof of it working correctly. So we can use this small signal voltage gain, or excuse me, this short circuit transconductance to calculate our small circuit voltage gain. And one of the reasons why the book emphasizes this method so much is because it readily shows us that increasing our output resistance will have an effect of increasing the magnitude of our voltage gain every time. So this is a short and quick way to recognize that whatever we can do to boost our output impedance will give us a better amplifier with respect to gain characterization. All right, so with that in mind, let's now get a bit more specific and look at the BJT Cascode Amplifier. So we're going to start with an amplifier that is being loaded by an ideal current source. And then we'll work on practical current source representations momentarily. But our Cascode amplifier, and specifically drawing here the NPN version, would look something like this. So we're going to apply a fixed voltage to the base of transistor 2, We're going to apply our input voltage to the base of transistor 1, and we are taking the output voltage at the collector of transistor 2. So we could interpret this in a couple of different ways. The first, since we're taking the input, or we're applying the input at the base and taking the output at a collector, it's going to be probably most easily compared to a common emitter amplifier with just another transistor thrown in there doing something, okay? Another way to interpret this would be to consider this as a common emitter amplifier with a common base amplifier stacked on top, right? So the output voltage of the common emitter amplifier would be taken at this node right here between Q1 and Q2, right? But we have replaced the resistor of that common emitter amplifier with a common base. So two different interpretations, both reasonably okay. We are going to apply the short circuit transconductance method of determining this guy's voltage gain. So with that in mind, we need to figure out what capital GM is, right? Unfortunately for this guy, it's not going to be as trivial as the last example. So if I'm looking at my small signal model for this guy, doing everything for transistor 2 first. So there's transistor 2. This is base 2, collector 2, and right here would be emitter 2. Oops, sorry, GM1, V pi 1, R naught 1. Here's R pi 1, V pi 1. So this is the base of 1, the collector of 1, the emitter of 1. And over here is where we would apply our input voltage, Vin, like so. Because we're looking at short circuit transconductance, that means I need to short my output node, which is found at the collector of transistor 2. And look at this current I out. And the reason why the ideal current source doesn't show up is because it has an infinite resistance. And so that would just be an infinite resistance or open circuit placed between this collector node and ground. So effectively, there shouldn't be anything there. So that's why I'm not drawing anything. So this looks particularly ugly, right? Pretty ghastly. But there's a couple of things that we can observe. The first of which is that the resistor R pi 2 is placed between this node. Let me circle it or highlight it in some other color or something like that. That's all one node. So R pi 2 is between that node and ground, as is R naught 2, as is R naught 1. So all three of those resistances are in series. or excuse me, in parallel, okay? So that's gonna let me redraw this guy in a little less horrifying of a form, all right? So I'm gonna redraw this guy and say, here is GM2 V pi 2 here is GM1 V pi 1. This is my resistor R01 in parallel with R02 in parallel with R pi 2. Which means, let me connect these guys real quick here, that this voltage, positive polarity on bottom, negative polarity on top, is V pi 2, because that bottom node is going to be ground, and we can see that the positive polarity terminal of V pi 2 should be connected at ground. Just to be super clear here, this node is going to be where collector 1 and emitter 2 are tied together. This is my ground, so this is representing where emitter 1 is, base 2 is, and collector 2 is. Here is V pi 1, R pi 1, here's the base of transistor 1, here's my input signal, and then the last thing I need to do here is have my short circuit like so. So I put all of my 3 resistors in parallel and simplified this guy as much as I possibly can, and I can make some observations with this particular representation that I feel are pretty straightforward. All right. The first thing that I can see is that I out is exactly equal to GM2 times V pi 2. And using Kirchhoff's current law, I can say that this is equal to GM1 times V pi 1 plus a current I'm going to call IX, where this is my current IX, the current that branches off and divides itself among those 3 resistors. All right. I can say that IX is equal to negative V pi 2 divided by those 3 resistors in parallel. And I can say that V pi 2 is simply I out divided by GM2. This is me rearranging this guy right here. So if I make those 2 substitutions into my original equation, what I get, and I'm running out of room, so let me do it on this next page, is that I out is equal to GM1 Vn minus I out divided by GM2 R01 in parallel with R02 in parallel with R pi 2. And rearranging slightly, I get I out is equal to GM1 times Vn times, in my denominator, 1 plus GM2 R01 in parallel with R02 in parallel with R pi 2. And up here, I just have GM2 multiplied by R01 in parallel with R02 in parallel with R pi 2. So this looks a little bit gnarly, but we could figure out what our short circuit transconductance is. It would just be this right-hand side divided by the N, right? Nothing real wild there. But because we're dealing with BJT technology, if we are not using discrete transistors, meaning that we were designing this to be manufactured for us, the transconductance of both of our transistors should be practically identical because they're both carrying the same amount of current, more or less, right? They're stacked on top of each other, and there is some bias current that's flowing through both of them. So we could argue that IC1 is going to be really darn close to IC2. Additionally, because they're fabricated identically, R01 is the exact same thing as R02 as well, right? Because they're going to have the exact same early voltage. And so what that means is that this whole big guy right here really just reduces down to GM1 times VN1, because we have some number that's reasonably large divided by 1 plus that same number. So it's going to be awfully close to this guy right here. So the short circuit transconductance of our cascode stage is approximately the transconductance of BJT Q1. All right, that's the assumption that we're going to make here, and that obviously makes the math much, much easier. The textbook kind of just explains it away and says, it's this. It seems incredulous, but it is. I've tried to do a little bit more rigorous of a job here. So from this, the voltage gain of our BJT cascode amplifier is negative GM times R out, which is just negative GM1. And our output resistance is just what we spent so much time calculating on Monday, right? So skipping ahead to the reduced form, we would have GM2 R02 multiplied by R01 in parallel with R pi 2 here. One thing that I do want to point out is that if we looked at our notes from Monday, the output resistance would have been GM1 times R01 times R02 in parallel with R pi 1. It's because in that portion, we were considering transistor 1 to be the one on top that was being degenerated by transistor 2. And for our cascode amplifier, we are considering transistor 1 to be the guy on bottom and transistor 2 to be the guy on top. So that's why there's a change in subscripts. I just wanted to be clear about that because that could seem confusing. All right, so we have our voltage gain, again, because GM1 and GM2 are effectively going to be equal, and R01 and R02 are going to be equal. We can say that this is negative GM1 squared R01 times R01 in parallel with R pi 2. So our gain then, as compared to a simple common emitter amplifier being loaded by an ideal current source, has been increased by a factor of GM1 times R01 in parallel with R pi 2. So we could probably observe that there's a pretty appreciable amount of gain, and that's actually the exact thing that we're going to do here in this next example problem. So let's say that we have these two amplifier circuits, both being loaded by an ideal 1 milliamp current source. So this guy is nothing more than a simple common emitter amplifier. And then our second guy, sorry, CC because it's a BJT. VB2, VN. Here is the out. And because I didn't write things down here, let's say that beta is equal to 100 and VA is equal to 5 volts for all of our transistors. So from this information, our transconductance for all of our transistors is going to be IC over VT is 38.462 millisiemens. Our early effect resistance, VA divided by IC, gives us 5 kiloohms, and our internal resistance R pi, beta over GM, is 2.6 kiloohms. So for our standard common emitter amplifier, our voltage gain is given by negative GM R naught, the intrinsic gain, since we have it loaded with an ideal current source, would give us a value of negative 192.308 volts per volt. And our cascode has a voltage gain of negative GM1 squared R01 times R01 in parallel with R pi 2 would give us a value for the voltage gain of negative 12,651.822 volts per volt. So 66 times as large of a voltage gain. A pretty dang appreciable increase in voltage gain. All right. So, right 1 milliamp here. This is really representing the maximum possible voltage gain that we could ever get out of one of these guys, or at least this equation represents it. Obviously, the value is going to change depending on things like the early voltage and the bias current and stuff like that. But in practice, we can never actually load these guys with an ideal current source because they don't exist. So what do you guys think we should do to represent a real current source? Any thoughts? Not remotely a trick question, just throwing that out there. Yeah, we're going to use another BJT, but we're going to use PNP BJT to do it. So my question to you guys is then, should we represent our practical current source with a single BJT or a cascoded BJT current source? Cascoded, why cascoded? Or do you have any idea other than? So it does have something to do with the degeneration, but let's look at this example just real quick, right? So if we had a current source, I'm going to call this guy R out, comma N, because it's the NPN side, and this guy over here would be R out, comma P, where we're putting our PNP transistor. We will replace that 1 milliamp source with a PNP current source of some shape or form, right? Using the short circuit transconductance method of calculating the voltage gain, it should be fairly obvious, actually, that we would just have GM1 multiplied by the output resistance seen looking into this terminal, which would be R out N in parallel with R out P. If we were to use a single BJT or PNP BJT as a current source, it has a very small output resistance as compared to the Cascode, right? And so we would see a small resistance in parallel with a large resistance, which looks smaller than the small resistance. Whereas if we went with Cascode, we'd have two large resistances or impedances in parallel. And so while our gain is going to go down, it's not going to go down nearly as much as if we had done a single stage. So the proper way to realize a Cascode amplifier then would look something like this. Let's see, put B out way over here. This is going to be Q4, Q3, Q2, Q1. So this is VB4, and this is VB3. So we have a PNP BJT current source on top. And then here we have VB2 and VN. So on bottom, we have a NPN Cascode amplifier. Just real quick, why is the short circuit transconductance of this guy gonna be just GM1 again? Anybody have any ideas about that? We've thrown two more transistors in there. Why don't they mess with it? Because the short circuit transconductance implies that this output terminal is shorted. So these resistors would be placed between ground and ground, meaning they have no effect. So, absolutely right. Just wanted to ask you guys. So looking up this way, again, we would have R out P, down this way, R out N, and we would see that our voltage gain AV is going to be approximately equal to negative GM1 times R out N in parallel with R out P, which is going to be negative GM1 GM2 R out 1 parallel R out 1 and parallel with R by 2. That quantity in parallel with GM3 R0 3 R0 4 parallel with R pi 3, where we can expect that R0 3 and R0 4 are similar in size because the same current is flowing through both of the PNP transistors and they would have the exact same early voltage as well. This guy right here, yes, that is GM2, but we should expect GM2 to be approximately equal to GM1. So really a better way to think about this would be the transconductance of the NPN transistor multiplied by the transconductance of the NPN transistor times the early resistance of the NPN transistor times the parallel combination of the early resistance and the internal resistance of the N side. And then everything over here is just the P values, where we are assuming that GM is the same for all the P types and the same for all the N types, but not necessarily identical to each other. So an N-type current source would be placed between this output node and ground, right? So we are trying to replace this current source right here, which is between VCC and the collector of transistor 2. So the PMOS is always going to be connected to the power supply. Its emitter is always going to be connected to the power supply, whereas the emitter of the NPN will be connected to ground. So we would have some weird floating, we wouldn't really be loading it, we would be placing it in parallel with it, if that makes sense. All right, we got 20 minutes left. I have an example here, but I'm going to skip it because we're running low on time. So let's talk now about the Mosfet Cascode Amplifier. And this is going to be real short. All right, so with Mosfet transistors, and I'm skipping where we're loading it with a ideal current source, our Cascode amplifier is going to look something like this. This is M4, M3. Here's where we're taking our output. M2, M1. All right, so this is VG4, VG3, V out, VG2, V in. So effectively the exact same thing, except we were realizing all of our NPNs with NMOSs, all of our PNPs with PMOSs. If we were to look at the small signal analysis of this guy, what would be the only fundamental difference between what we had with the BJT circuit? We'd have open circuits wherever we saw R pi. So from that, our short circuit transconductance would be GM1, GM2 multiplied by R01 in parallel with R02 divided by 1 plus GM2 R01 in parallel with R02, and this is approximately equal to GM1 if 1 over GM2 is much less than R01. We have to make a condition here, and it's because in a Mosfet transistor, the designer can choose the widths and the lengths of the transistor's channel, which will directly influence the size of the transconductance as well as the size of the channel length modulation coefficient, right? So we don't have the guarantee that we had previously where the transconductances were going to be roughly equal and the early voltages were going to be exactly equal when we deal with MOSFETs. So it's only going to look like GM1 under this particular condition. Our voltage gain then, where we would consider everything up here to be R out P and everything looking down to be R out N, is given by AV is negative GM1 times GM2 R01 R02 in parallel with GM3 R03 R04. And again, all three of these transconductances can be different. All four of those channel length modulation resistances can be different because the size of the transistors can easily vary just depending on what the designer chooses. So can't really simplify this guy any further. Its behavior other than that is exactly the same, right? So any questions on the Mosfet Cascode Amplifier? Did everything with one picture and three equations. We beat the BJT one to death. All right, nobody's saying much of anything, so let's introduce the concept of current mirrors. And we are going to start by discussing temperature and supply dependence of bias currents. So let's start by looking at a BJT circuit. And I'm just doing these dots or ellipses or whatever you want to call them right here to signify that we don't have an open circuit. We are connected to some sort of load so that there is not an open circuit for current to flow, okay? This is our base emitter voltage, VBE. And so for some negligible base current, we can say that VBE is equal to VCC times R2 over R1 plus R2. That's just using voltage division, nothing wild or crazy there. Is equal to VT times the natural logarithm of I1 over IS for this particular transistor Q1. So there's really two problems here with why we might have issues with that current I1. The first of which is the bias point voltage of our transistor Q1 depends on the power supply voltage. If there is a variation in the power supply voltage, meaning if VCC were to decrease, that means I1 has to decrease also, which might result in everything connected to that node being not operating correctly. So think about it in this way. you have a cell phone. I'm sure every single one of you has a cell phone, right? So does your cell phone still function when the battery is fully charged and when it is near to being completely discharged? It has roughly the exact same functionality. The voltage drop over your battery has changed. Typical cell phone batteries have a nominal 3.3 volt voltage. So when your battery is fully charged, it's really somewhere around 3.4 to 3.45 volts. And when it's really close to being fully discharged, it's probably somewhere around 2.9 to 3.0. So if your cell phone relied on this type of biasing to where the amount of current that was being supplied to your different chips and all that kind of stuff varied with the supply voltage, you could never use your cell phone once it got below a certain state of charge. It would be a very terrible design. So biasing in this way is actually really bad for high performance microelectronics because the supply voltage can vary appreciably, especially for portable products and stuff like that. Now let's consider what happens if this circuit experiences a temperature change while it is operating. So let's say that VCC is very stable, but the temperature changes. We should know by this point in our EE careers that the resistances are going to change. However, if the resistors are made out of the same material, R1 is going to increase by the exact same amount or fractional amount as R2. So we should see that our voltage VBE is constant even though the temperature changed, assuming R1 and R2 are made of the same materials. However, our current depends on our thermal voltage, which obviously is going to change when the temperature changes, and this saturation current IS, which is also temperature dependent. So when the temperature changes, even though the DC bias voltage doesn't change, we're going to see that the amount of current changes as well. So this simple scheme, which is what we did so much of in 335, is fantastic for very simple and trivial amplifiers, but really, really bad for any kind of quality electronics. If we looked at a Mosfet circuit, we would see roughly the same effects. So here's R1, here's R2. This would be VGS. Here's our drain current, I1, 4 transistor M1, and we've got it connected to some sort of load. Assuming we have saturation region operation, I1 is 1/2 mu n Cox W over L, VGS minus VTH quantity squared, where we're neglecting channel modulation. And because of our resistive biasing we have here, this is going to be exactly mu n Cox W over L times VDD R2 over R1 plus R2 minus VTH quantity squared. So again, if our power supply voltage varies, our current I1 varies, and mu n and the threshold voltage all depend on temperature. So we again see very similar instabilities due to the dependence of our biasing current I1 on both the supply voltage and the temperature. In order to generate supply and temperature independent voltages and currents, we actually have to use a much more robust circuit that uses a quantity that is temperature independent in order to operate. The most common one that is used is what is called the Bandgap reference circuit. So I have a Bandgap reference circuit designed by the engineers at Samsung, shown here. This was designed, or at least they published it in 2008, capable of generating a reference voltage, which we can see actually varies a fairly good amount with respect to temperature, and a reference current, which is actually fairly stable with respect to temperature. So it's somewhere around 50.25 microamps from an operating range of less than 0 degrees C up to 100 degrees C. This guy's a monster. Okay, let's start there, okay? Anybody notice anything particularly terrifying about this guy? Where do you start? Okay, the thing that terrifies me the most, so everything up here is Mosfets. And then there's a couple of buffer amplifiers or inverters. Yeah, actually these are inverters. That's trivial enough to do with Mosfets. You guys had to do it. We got a BJT and a BJT. So it is a mix of BJT and MOSFET technology, which means in order to design this circuit correctly, you have to intentionally include parasitic BJTs into your CMOS design in order to make this guy work. That isn't wildly difficult, but it is a bit of a pain in the butt. This type of circuit is well beyond the scope of this class. It's beyond the scope of what we do in 438 to be entire. This is a graduate level problem of designing temperature and voltage supply stable references, okay? And your textbook literally says, this crap is too hard. Let's move along. So this is an incredibly useful circuit, but it's also pretty darn big too, right? It's got tens or more of transistors. It's got digital logic in there. It's got all kinds of weird and wild stuff, right? If we had to use this every time we wanted to get a current source in our microelectronic circuits, we couldn't have phones and things like that the size that we have them today. They would be as big or maybe bigger than the bricks that we had when Ronnie and I were growing up, because we're old as shit. Sorry to throw you under the bus. So instead, what is done is what's called current mirroring, okay? So in a current mirror, we have some reference current, typically supplied by a Bandgap reference circuit like the one we just saw, or something similar, just depending on the application. And then we feed this into a specialized circuit, which is called a current mirror. And what the current mirror does is it senses what the value of the reference current is and then makes a copy of it. And we can use current mirrors to make multiple copies of that same reference current, so that if we have one stable source of a fixed current, we can apply that exact same current all over, or as many times as we need, through a larger microelectronic circuit. So what we're going to spend Friday talking about, because we only got a couple of minutes left here, is how to realize the current mirror using both BJT and CMOS or MOSFET technologies, as well as how we can scale them, right? Because we might have different parts of our circuit that require a bias current that isn't exactly equal to IREF. So we have to figure out mechanisms by which we can make our copy, say, 5 times as large or only half as large or things like that, based on what the application calls for. So we can use this current mirroring technique to generate copy currents all over our larger circuit that are all going to be effectively just as stable as the one supplied by our Bandgap reference, without having to copy the Bandgap reference circuitry itself. All right, so that's enough out of me for today. like I said, class on Friday will hopefully finish up the concept of current mirroring, or at least as it's required in this class. So in 438, we spend about a week talking about current mirroring because you guys are only going to learn about simple. We talk about Cascode, Wilson current mirrors, all kinds of crazy stuff in 438. But for this class, you just learn the very, very basics. So we should be able to finish that in a day. All right, see you guys on Friday. Don't forget that your quiz is due next week, next Wednesday or something like that. And your first project should be due reasonably soon as well, right? Yeah. Okay, so don't forget about those things. All right, see you guys later.